So, today I will start the second chapter. The second chapter is linear differential equation. We will discuss in this chapter generalities, some general properties of linear equations whose coefficients can be functions of x, they are not constant coefficient equations. The theory of constant coefficient equations we will take up in the next chapter. These are general things that hold for all linear differential equations. So how does a linear differential equation look like? It's a nth order equation a naught y plus a1 x dy by dx plus etc plus an minus 1 x n minus first derivative plus the nth derivative, right, the last term. Observe that the coefficient of the top order derivative is 1. We say that the differential equation is in normal form. If it is not 1, then you have to divide by the coefficient to bring it to normal form. Okay. So, the functions a naught, a1 up to an minus 1 and b, they are assumed to be continuous on some fixed interval on the real line. That is the assumption that we are going to be making. So, you are going to work on a fixed interval of the real line, and on that interval we are going to assume. The case when bx is identically 0, we would call it a homogeneous linear differential equation, right. So, this is the setup for the whole chapter. Frequently we will work with case when n equal to 2, not because it is simpler, because it is easy, notationally it becomes easier to work with. For nth order equation, the notations become more cumbersome, but there are no new ideas involved. So, we begin with the homogeneous linear ODE, which is nth derivative of y dny by dx to the power n plus sigma j from 0 to n minus 1 ajx the jth derivative of y equal to 0. So, this is a homogeneous linear. Now, if y1 and y2 are two solutions, then it is immediate that c1 y1 plus c2 y2 is also a solution. It is completely obvious, you simply substitute and check. So, this means that the set of all solutions of a homogeneous nth order linear differential equation is a vector space over the real numbers. If the coefficients take values which are complex numbers, then we will talk about complex linear combinations, then we will allow the C1 and C2 to be complex and it will become a complex vector space. There is no difference, just a question of whether we are allowing the coefficients C1 and C2 to be complex numbers or not. Okay. The dimension of this vector space is n. However, this is not easy to see. Suppose you take a simple example, y double prime plus y equal to 0. Sin x and cos x are solutions, and so are C1 sin x plus C2 cos x. How do you know that there are no other solutions? It is not entirely obvious. Even in the second order case, it is not so easy to show that any solution is going to be a linear combination of a sine and a cosine. In courses, one tends to take these things for granted, but when you really begin asking questions, then you slowly begin to realize that even an innocent looking thing like a second order ODE is not so, answers are not so obvious. You need to do a lot of work to get. Now, many of the well known equations in mathematical physics assume this form dny by dx to the power n plus sigma j from 0 to n minus 1 ajx dj y upon dx to the power j. What I had displayed turns out to be the story for many of the important examples arising from physics. Most of the equations in mathematical physics are linear homogeneous differential equations. So I am going to now give you a big list of such equations, and please write them down because they are very important. The first one is the Legendre's differential equation, 1 minus x squared y double prime minus 2xy prime plus p into p plus 1y equal to 0. This differential equation is known as the Legendre's equation. Right? P need not be an integer in any of these things. The second one is called the Chebyshev's equation, 1 minus x squared y double prime minus xy prime plus p squared y equal to 0. The third one is called the Airy's equation, and the fourth one is the Hermite's equation. The next one is the Laguerre equation, xy double prime plus 1 minus xy prime plus lambda y equal to 0. Then comes a very important equation, the second most important in this whole list is the Bessel's equation. The most important one is the Legendre's equation, then the next second most important is Bessel's equation. X squared y double prime plus xy prime plus x squared minus p squared y equal to 0. When I say important, I mean from the point of view of engineering, when you are going to be teaching students of engineering. So from the engineering point of view, the most important one is Legendre and the next is Bessel. Mathematically, from the point of view of mathematics, the most important equation is the hypergeometric equation. From the mathematician's viewpoint, the hypergeometric equation is x into 1 minus x y double prime plus c minus a plus b plus 1 x y prime minus a b y equal to 0. This is called the hypergeometric equation. Very similar to the hypergeometric equation is Jacobi's equation. Now, I do not know whether you have seen these equations before, and would you like to tell me where you have seen them or why are these important? What is the significance of these things? Why should we teach students the Legendre's equation? Very likely you have taught them series solutions of ODEs, right? For series solutions of ODEs, you take the Legendre's equation as a illustrative example. So where does the Legendre's equation come from, and why is it important, and what does the P signify? I think if you have never done this, I think it will be very important to do this. Look up this Robert Resnick's quantum physics. Or Arthur Beiser, Perspectives of Modern Physics. Perspectives of Modern Physics, where they have given a very detailed account of the Schrodinger's equation for the hydrogen atom. Right? Now, what does a hydrogen atom consist of? A proton, right? And the Schrodinger's equation, how does the Schrodinger's equation look like? It contains a Laplacian term, right? Del 2 by del x squared plus del 2 by del y squared plus del 2 by del z squared. It is a partial differential equation. It is a partial differential equation. It involves, in the heart of the equation, you see the Laplacian term, correct? Well, because there is a hydrogen, because of the spherical symmetry of the hydrogen atom, there is only one proton, and then you will see that there is the space around it should exhibit some kind of a spherical symmetry, and so it is very natural to write down the Schrodinger's equation in spherical polar coordinates. And then if you look at these books like Resnick or Beiser, you will see that this partial differential equation is solved by the method of separation of variables, and you get 3 ordinary differential equations. One of them is the Legendre's equation, and the P that you see there is related to the quantum numbers. So, this is all that I will say about this equation, and I think it is up to you to go further into this and probe further into this matter and learn more about this. Probably in the PDE course you will see more details on these matters. In general, I will say the following: when you look at physical phenomenon, they will be governed by partial differential equations. Physical processes are governed by PDEs, heat conduction, wave propagation, etc. I mean, you take a circular metallic drum and set it into vibrations, all sorts of physical phenomena, they are governed by partial differential equations. And the homogeneity of space would demand that the solution should be translation invariant. And the differential equation will be a constant coefficient differential equation. Isotropy, that is, it is the same in all directions, would imply rotation invariance. And if it is if a differential equation with constant coefficient differential equation is rotation invariant, that is, if u of x is a solution, u of Rx is also a solution where R is a rotation matrix, then the differential equation basically is a polynomial in the Laplacian. That is why you see the Laplacian appearing in the Schrodinger's equation, the heat equation, the wave equation, the biharmonic equation. All these equations of mathematical physics, if you look at, there's somewhere the Laplacian operator is sitting there. It is one of the most important operators. The Laplacian is one of the most important operators. And if you write down the Laplacian in spherical polar coordinates, the Legendre differential equation is bound to pop out of it. And if you write down the Laplace's operator in cylindrical coordinates, suppose for example you are looking at skin effect, you have some current flows through some long cylindrical conductor, there is a skin effect, right. So that you will write, you can study the skin effect, and you will write you will employ the cylindrical coordinates because the system exhibits cylindrical symmetry. Now you write down the Laplace's equation in cylindrical coordinates, and the Bessel's functions, Bessel's ODE is bound to pop out. That is why you see when you open books on engineering and mathematical physics, you see it is full of Bessel's functions and Legendre functions. For example, you are studying diffraction gratings, let us say diffraction through a circular aperture, Bessel's functions are going to show up. You are studying Newton's rings, right, in physics. What are the radii of these successive Newton's rings? There are zeros of Bessel's functions. So Bessel's functions and Legendre functions are exceedingly important. They are by far the most important functions of mathematical physics, and these are that is why I said that the Legendre and Bessel are the most important functions for an engineer. Of course, for a mathematician things are different. For a mathematician, the hypergeometric equation, any mathematician will argue that the hypergeometric equation is the most important equation. The hypergeometric equation is important because it encompasses all the special functions in some form or the other. That is the reason. That is one of the reasons. There are several reasons one can give, but that would be a good enough reason to say that that is one of the most important equations. Okay. All right. So let us proceed further. So now let us now turn our attention to second order ODEs, y double prime plus pxy prime plus qxy equal to rx. Much of what I say, pretty much everything that I say will generalize to equations of higher orders also. So now suppose that yx is a solution of 2.1 with rx equal to 0, the homogeneous case, the homogeneous case. So assume that Rx is 0 and assume that you have a solution Yx of 2.1. Assume that the solution vanishes at a point and the derivative also vanishes at the same point. I am looking at a second order equation, remember, homogeneous linear second order ODE, and I had taken a solution y, I am giving you a solution y, and I am also telling you that the solution vanishes at a point and its derivative also vanishes at the same point. Then what is the conclusion? That is the 0 solution. So if you know that the solution and the derivative both vanish, then it is the 0 solution. Now if this particular differential equation were to be equation governing a mechanical phenomenon, such as a harmonic oscillator for example, then what the theorem is saying is that if the position and velocity at a point vanishes, then the that is a 0, then it is a 0 function. The position and velocity simultaneously vanish, then it is 0, the solution is a 0 solution, that is what it is in the mechanical system, but it does not have to be a position and velocity, it may not be a mechanical system, it could be something else. Okay, so now let us get to the proof of this. The proof is not easy, so please pay full attention, and if you are writing down, write it down, sure, but I do not mind going slow. It is the theorem is non-trivial, it is a first non-trivial theorem we are going to be proving in this course. So let us take a point in the interval x1, any arbitrary point. We have to show what? We have to show that y vanishes at that point, correct? Okay. So let us set up, let M be the supremum of mod P and mod P plus mod Q. What is the meaning of supremum? The least upper bound. Supremum means the least upper bound, and I had taken an x0 and an x1 in an interval I. All functions concerned are continuous on the interval I, and so now on the closed interval x0 to x1 a continuous function is always bounded, correct. So mod P is bounded, mod Q is bounded, mod P plus mod Q is bounded. So I take the supremum of that function, call it M. We are going to take it does not have to be the least upper bound, any upper bound will do the job, will be enough for our purpose, okay. So I just written take the supremum, is that okay. After you do this supremum, we are going to introduce a function called the energy function. Let us introduce into our study the energy function Ex. How do I define this energy function? I simply define it as square of y plus square of the derivative, yx squared plus y dot x the whole squared, and I am calling it the energy function. Whether or not it represents the physical energy is irrelevant for our purpose. If it is a harmonic oscillator, it is indeed the energy, the sum of the kinetic energy plus the potential energy. So it is in some sense an energy like function, okay. And let us differentiate the energy function. Okay, so differentiated E dot, what are I going to get? 2y dot, right, y squared I have, so I got 2y dot plus 2y dot y double dot, but y is a solution of a second order ODE. So y double dot is minus py dot minus qy, correct. So write it down. So equal to 2y dot y plus 2y dot into minus py dot minus qy. Recall that we are looking at the homogeneous scheme. And now you see, I am saying that whole business out there is less than or equal to, we are in the third line, we are right here. So is it correct to say that y dot y is less than or equal to mod y dot? Of course, any number is less than or equal to modulus the number. And I have taken the modulus of all the terms on the right hand side. 2 y dot into mod, you take mod of that, 2 mod y dot, mod p, again a mod y dot. So you have a y dot squared, and then mod p is less than or equal to m, and that is how I get the 2m y dot squared. Third term is going to give you what? There is a q there, right, and mod q is also less than m. So I am going to get 2m into mod y dot. Okay, so far everything is fine. Now that is less than or equal to, I combined the two all the y dot business together, I am getting a coefficient 2m plus 2, correct, and then there is a 2m y dot squared, and I add to it a y squared. Sure enough, that is possible. I am putting a less than or equal to sign, fair enough. Now what have I done in the next line? 2m plus 2, I replaced y dot by y squared plus y dot squared. Why? A squared plus b squared minus ab is always positive, isn't non-negative, isn't it? Ab will always be less than or equal to a squared plus b squared. That inequality you are familiar with? It's not Cauchy or inequality, it does not matter. Okay. Basically AB less than or equal to a squared plus b squared, right. Yeah, that's, so you get the mod y dot has been replaced by y squared plus mod y squared plus y dot squared, correct. So now all in all, what do you get? Put combine everything, you get a coefficient 4m plus 2. That is a constant, I do not care, as long as it is a constant I do not care. And then what is left over? Y squared plus y dot squared, that is the energy function again. So we have proved the following inequality. What have we got? E dot less than or equal to constant times E, and that constant is 4m plus 2. This is called a differential inequality, not a differential equation, but a differential inequality. We arrived at a differential inequality. Had it been an equation, had it been E dot equal to 4m plus 2E, then how would you solve that equation? It would be a linear, homogeneous, linear first order ODE. And what is its integrating factor? E to the power minus 4m plus 2x, correct? You use the same integrating factor, does not matter, although it is an inequality. So what? That exponential function is never is always positive. So I can multiply the inequality by the exponential function. No harm, nothing is going to happen. What is going to what do you get if you do that? Since many of you are writing down, you can write it down and then tell me what you get. Multiply the inequality itself by e to the power minus 4m plus 2x, bring everything on the left hand side and then tell me what do you get. ddx of, yeah, please work it out. Multiply the differential inequality by the exponential of minus 4m plus 2x. Bring everything, bring all the terms on the left hand side, and the left hand side becomes a perfect derivative. So tell me it's a derivative of what? So we will get ddx of Ex e to the power minus 4m plus 2x, that business is less than or equal to 0. That is what we arrived at, correct. Now integrate this from x naught to x1, integrate this equation from inequality from x naught to x1, and what do we get? We get Ex1 of e to the power minus 4m plus 2x1 less than or equal to Ex naught of e to the power minus 4m plus 2x naught. But what is E of x naught? What is our condition? That y of x naught is 0 and y dot of x naught is 0, which means that E of x naught is 0. So what are we left with? Ex1 e to the power minus 4m plus 2x1 less than or equal to 0. Anyway, it is also greater than or equal to 0 because energy, the way we have set it up, is always a positive function, non-negative function. So what do we get? We got that the energy is 0, which means that y of x1 is 0. I have finished. The proof is over. This method you will not find normally in books. Standard books will not have these things. You will not find this in Kreyszig or Boyce de Prima or any of the books. This is not normally. This is not the way you would prove this theorem in ODEs. This theorem is normally proved by appealing to the fundamental existence uniqueness theorem. But I have chosen to give this argument. This argument is much more frequent in partial differential equations. This is called the energy principle. This is used so frequently that this is not a trick. It has been elevated to a principle. I would call it the energy principle. You can use the same idea to show the uniqueness of solutions for a wave equation or for a heat equation. The initial value problem will have unique solution. You can use the same ideas to carry out those, to study those equations. A large class of evolution equations in partial differential equations. So the method is very important. The results can be the same result could have been arrived at by different ways, by appealing to the fundamental existence uniqueness theorems, but that is not what I am looking at. This particular technique is important, the energy technique. Okay, you might ask, all right, fine, we have proved a theorem that if a solution and its derivative simultaneously vanishes, then the solution must vanish identically. Okay, so you might ask, well, you have proved a nice theorem that if the function and its derivative vanish, if the solution and its derivative vanishes at a point, then it must be the zero solution. Who cares? Well, we care because this gives you the uniqueness theorem for. So if y1 and y2 are two solutions of y double prime plus py prime plus qy equal to 0, where p and q are functions of x, and if y of x naught equal y1 of x naught equal to y2 of x naught, y1 dot of x naught equal to y2 dot of x naught, then y1 and y2 are identical. Two solutions which agree at a point and whose derivatives also agree at a point, they are one and the same. In other words, specifying the function and its derivative at a point uniquely determines the solution. Once you have the theorem, the corollary is easy to prove. You look at the difference y1 minus y2 and apply the theorem. Y1 minus y2 is also a solution as you are looking at a linear differential equation, homogeneous linear differential equations, solutions from a vector space. So if y1 and y2 are solutions, y1 minus y2 is also a solution, and this solution vanishes at x naught, the derivative also vanishes at x naught. So there you are, it must be the zero solution, so y1 must be equal to y2, finished. So it gives you, so we have proved uniqueness. Next corollary, the vector space of solutions of y double prime plus pxy prime plus qxy equal to 0 cannot have dimension greater than or equal to 3. That is, the vector space of solutions has dimension at most 2, and then after that we will have to show that the dimension is at least 2. So, that the and then combining the 2, you will conclude that the dimension is exactly 2. That would be the way. So, I raised this question some time ago, right? Y double prime plus y equal to 0, harmonic oscillator. Sin x and cos x are solutions. How do you know that every solution is of the form C1 sin x and C2 cos x? Well, sin x and cos x are already linearly independent, and now I have shown that the dimension cannot exceed 2. So, it has to be exactly 2, finished. So, the case is completely settled for a harmonic oscillator, right. Well, let us go to the proof of this. Has everybody understood the statement? Okay, so let us compute. So, we have to show that the dimension is less than or equal to 2, which means that if I take 3 solutions, they are linearly dependent. So, let us take 3 solutions y1, y2, y3, and let us look at the vectors y1 x naught, y1 dot of x naught, y2 of x naught, y2 dot of x naught, y3 of x naught, y3 dot of x naught. These are 3 vectors where there are 3 vectors in R2. Every one of them is an ordered pair, and I am evaluating the solution at a point, no, x naught. So, the components are constants, they are not functions. So, I am having now 3 vectors in R2. So, any 3 vectors in R2 are linearly dependent. So, there exists constants C1, C2, C3, not all of which are 0, such that the linear combination is equal to 0. That is, C1 times y1 x naught, y1 dot x naught, plus C2 into y2 of x naught, y2 dot of x naught, plus C3 into y3 of x naught, y3 dot of x naught is 0. Correct. So, now let us look at y of x equal to C1 y1 plus C2 y2 plus C3 y3. Let us look at y of x equal to C1 y1 plus C2 y2 plus C3 y3. That is also a solution of our ODE, correct. Calculate its value at x naught. What are you going to get? What is y of x naught? C1 y1 of x naught plus C2 y2 of x naught plus C3 y3 of x naught. What is that? 0, correct, because of this condition, correct. And the same thing is the case for the derivative also. So, once again we can appeal to the theorem and we conclude that the function should be identically 0, that is C1 y1 plus C2 y2 plus C3 y3 is identically 0. And C1, C2, C3 are not all 0, therefore they are linearly dependent. So, we have proved that any 3 solutions are linearly dependent. Yeah, I can see that some people, it is getting a little heavy and theoretical. Some people are just woken up from their sleep, some people are sleeping, some people are on the verge of sleeping, some people are fighting their sleep, and some people are wondering, oh God, when is it all going to end, right. And yesterday it was all terribly easy, correct. You are all teaching this to 11th standard students, but suddenly you realize that things are escalated in difficulty. It is a fact that the dimension of the space of solutions of y double prime plus py prime plus qy equal to 0 is exactly 2, but this is not trivial. we need to appeal to the fundamental existence uniqueness theorem. Essentially, what is going on is the uniqueness part shows that the dimension cannot exceed 2, and the existence part tells you the dimension is at least 2. So, the two of them combine to show that the dimension is exactly 2. The uniqueness part we are done using the energy method, existence part we are not done. We have to cook up two linearly independent solutions. It's not easy, it's not difficult, but it's not easy either. You will have to use analysis, you will have to define, you will have to set up an iteration scheme and prove that it converges. That is the only way to do it. There is no shortcut in this generality. Okay. So at the moment we shall not prove that the dimension of this vector space is exactly 2. This follows immediately from the fundamental existence uniqueness theorem for systems of ODEs, right. But we have proved one half of it. We have showed that the dimension is at most 2. That part we are fixed up completely. Okay, the next thing is Wronskians. So, this is probably familiar to you from the linear algebra part. So, what is a Wronskian? Given n functions y1, y2, yn that are n minus 1 times differentiable, we define the Wronskian to be a certain determinant. What is a determinant? y1, y2, etc., yn, y1 the derivatives, the first derivatives from the second row, the second derivatives from the third row, and the n minus first derivative from the last row. Okay. Here it is up on display for you. So, now we have the Wronskian up on display for you. Now, what is the use of Wronskians? Linearly independent. So, then the next theorem, then the next obvious theorem. So, suppose the Wronskian is not 0, then the functions are linearly independent. Well, how do you show that? Suppose there exist constants C1 and C2, Cn such that C1 y1 plus C2 y2 plus Cn y1 yn is a 0 function. That is, it's a, yeah, I hope you are done vector spaces in your linear algebra part. So, some of the examples of vector spaces are functions, right, space of functions. So, here when I say that y1, y2, yn, when I want to show that y1, y2, yn are linearly independent, I am thinking of them as functions. So, suppose there is a linear combination which is 0 as functions, that it is a 0 function. Then I can always, then I have a nice equation which holds for all x, and I can differentiate it n minus 1 times. What comes out? It is a system of n equations. There I can think of them as n linear algebraic equations for C1, C2, Cn, and whose coefficient determinant matrix is what? The determinant is exactly the Wronskian, and the Wronskian is not 0. So, Kramer's rule from linear algebra tells you that it must have a unique solution, and that unique solution is exactly the 0 solution. And so, that is it, that is the proof. So, let us go through the argument again. So, suppose we want to show that given that the Wronskian is not 0, we want to show that the functions y1, y2, yn are linearly independent. So, assume there exists scalars C1, C2, Cn such that C1 y1 plus C2 y2 plus Cn yn is identically 0, it is a 0 function. Then you differentiate this n minus 1 times and you produce n minus 1 new equations. So, all in all you have n equations. We can view them as linear algebraic equations for C1, C2, Cn, and the coefficient matrix is exactly the matrix of consisting of the functions and their derivatives in succession, and the determinant of this matrix or the coefficient matrix is exactly the Wronskian, and what is given to me, Wronskian is not 0. So by Kramer's rule the solution is unique, and what is that solution? 0 is an obvious solution and 0 is the only solution. So C1 y1 plus C2 y2 plus Cn yn equal to 0 implies C1 equal to 0, C2 equal to 0, Cn equal to 0. That shows that the functions are linearly independent. What about the converse or contraposition? The Wronskian is identically 0, then the functions are linearly dependent. That is the converse, right? That is a statement of the converse. Is it true? Is it true that if the Wronskian W of y1, y2, yn is identically 0, then y1, y2, yn are linearly dependent? What do you think? What do you feel? It should be true. Anybody says it's not true? How would you prove it? Suppose I take the Wronskian of x cube x to the power 4. Now the Wronskian will be 0 at the origin. So at any point won't do. I am saying, I am giving you more data, no? I am saying that the Wronskian is identically 0. I am not saying that the Wronskian is 0 at a point. I am saying that you assume that the Wronskian is identically 0. Question: are the functions linearly dependent? No? Haven't you seen this any time? Answer is no. The converse is false. The converse is false. Okay. Yeah. So here is for those of you who are writing down notes, here is the complete argument for the previous theorem, that which I spoke the theorem, but now I have spelt out the proof of the theorem, but now if you want to jot down a few things, you can. Here is an opportunity for you to jot down. And the fact of the matter is that the converse is false. That is to say, if y1, y2, yn are n functions whose Wronskian is identically 0, it does not follow that the functions y1, y2, yn are linearly. Now what should we do now? We have to produce a counter example. Okay. Can you think of some examples? If you take a constant function, suppose okay, one function could be taken to be constant. You can't take two functions that are identical. That doesn't really work. Then you will not get the counter example. Suppose I take the constant function 1 and I take the constant function 2, they are linearly dependent. What do you want? You want a pair of functions for which the Wronskian is 0, but the functions are linearly independent. So you are allowed to take one constant, the other one has to be non-constant then. Okay, let us look at the example. y1 of x is x to the power 4 if x is positive, 0 if x is negative. y2 of x is 0 if x is positive, and x to the power 4 if x is negative. What is the Wronskian of these two functions? What will happen to the Wronskian of these two? On the positive real line, y2 is identically 0, right? So one of the rows of one of the columns of the Wronskian will be 0. So finished. On the negative real line, y1 is identically 0, right? And at the origin, both the functions are 0. So the Wronskian is always 0. Are the functions linearly independent or dependent? How do you show that they are linearly independent? Do it. So assume that there exist constants C1 and C2 such that C1 y1 plus C2 y2 is identically 0. Put x equal to 1. What do you get? Put x equal to 1. You get C2 is 0 and then put x equal to minus 1. After that put C2 equal to, after that put x equal to minus 1. Get the other constant is also 0. So the two functions are linearly independent. Correct? So be careful. What is the correct statement? The Wronskian is not 0. The functions are linearly independent. However, we have the following theorem. If y1, y2, yn are solutions of a homogeneous linear differential equation, then y1, y2, yn are linearly independent if and only if the Wronskian is not 0. What I am saying is, to make the converse is true, but if you know in advance that the functions are solutions of a homogeneous linear ODE, if you already know that, if you know that they are solutions of an homogeneous nth order ODE, there are n functions given to you and you have to give me an nth order linear ODE of which these are functions, then the Wronskian completely determines whether or not they are linearly independent. Wronskian not equal to 0, linearly independent, conversely it is also the case. Right. Is it clear? Any other questions? So let us illustrate the whole process. Let us illustrate the proof by working with a second order ODE. So we have already proved that the Wronskian is not 0 implies y1, y2, yn are linear. That is done. Half of it is done. The other half, that is, other half we will just do it for 2 by 2 case. The n by n case will follow very similarly. We need to do the energy business for the n by n case also. That is the way to do it. So suppose y1, y2 are linearly independent. Okay, second order case, and assume that the Wronskian is 0 at some particular point x naught. I am giving you its, identically 0, right? But here, okay, so all that we really need here is it's 0 at a specific point for some x naught. That means what? That means that the 2 by 2 determinant is 0 at the point x naught. When is a determinant 0? When its columns are linearly dependent. That means that there will be constants C1, C2, at least one of which is not 0, such that C1 times the first column plus C2 times the second column is 0. Correct? But then look at the function y of x equal to C1 y1 plus C2 y2. That is also a solution of the ODE. And what happens at x naught? It is 0. And what happens to the derivative? That is also 0. Finished. By the energy theorem, yx is identically 0 and so y1 and y2 are linearly dependent, a contradiction. So now you are beginning to see the importance of the energy theorem. Okay, finished writing? What? Oh, I should look at this so that it comes back on the. Okay, now it's come back. Now you can write. Yeah. The energy, yeah, the energy theorem. We are using the energy theorem to prove this. So for proving the nth order case, you will have to modify the energy theorem and get define the energy suitably for the nth order case. That can be done, but that will be more cumbersome. I mean, you will have to. It will be more notation heavy.
Is that like for those exact equations we had some differential forms, important differential forms? Like we have some energy functions.
No, we don't. I mean, there are too many of them. There are too many. That how to construct the energy function, that is you will get only by practice. You have to work with these objects. From when you learn PDEs, it will become really second nature to you. How do you construct the energy function? Because it was a second order equation, it is y squared plus y dot squared. If you take nth order equation, something else, the quadratic ones will generally work. Generally, you try the quadratic one. In the nth order case, you will have to try the energy function as y squared plus y dot squared plus y double dot squared plus right up to n minus 1 derivatives. Right. So have you finished writing this? Okay. So that says that the converse is true when the functions y1 and y2 are solutions of a homogeneous linear ODE. All right. Okay. Next, we come to a very important formula called the Abel-Liouville formula. This is the same Niels Henrik Abel, whose name you encounter, right, in group theory, abelian groups. You encounter the name of Abel in Galois theory, right, the Abel-Ruffini theorem. Yeah, and that if you in the theory of infinite series, the Abel's limit theorem in power series, the same Abel. In fact, the name also appears in the Old Testament. So let y1, y2, yn be n solutions of the homogeneous first order, homogeneous nth order, it's not first order, homogeneous nth order linear ODE yn x plus sigma j from 0 to n minus 1 ajx y super jx and wx be their Wronskian. Then wx equal to wx naught x of minus integral x naught to x a n minus 1 t dt. In particular, the Wronskian vanishes identically or never vanishes. The importance of this theorem is that even if you do not solve the differential equation at all, even if you do not know the functions y1, y2, yn, you can still calculate the Wronskian by knowing the one of the coefficients of the differential equation. This is in some sense, this is a very remarkable formula of Abel-Liouville, the Abel-Liouville formula. It has a lot of geometric content also. So in particular, it also says that the Wronskian is always 0 or it is never 0. If it is 0 at a point, then it must be identically 0, because the exponential function, second factor, is always positive. So let us look at the proof of this theorem. Right. So write down the Wronskian Wx, which is the Wronskian of y1, y2, yn, which is the determinant of nth order. Idea is to obtain a first order ODE for W. So how do you differentiate a determinant? How would you differentiate a determinant? You have a determinant, right? You have a determinant whose entries are functions. Row wise. It is the same thing. You can either do it column wise or do it row wise, because yeah. So what is the rule? So suppose I take an n by n determinant whose entries are functions of a single variable x, and I want to differentiate. After I calculate the determinant, I am going to get a function, and I want to compute ddx. I want to compute ddx of wx. So how do I calculate it? First differentiate the first row only and leave the remaining rows as it is, plus another determinant where you leave all rows intact except the second row, you differentiate the second row, and so on. So I will get the sum. So the derivative of a determinant will be a sum of n determinants. Okay. So here it is. So recall the rule for differentiating a determinant. I mean, I illustrate the case with a 3 by 3 example. I am illustrating it with a 3 by 3 example. The derivative is the sum of 3 determinants. It should be x because we have been using x all along. So x d dx of the 3 by 3 determinant. So apply this to the Wronskian, correct? Apply this rule to the Wronskian. What is going to happen? You see, if I differentiate the first row of the Wronskian, then the first 2 rows will be identical. If I differentiate the second row, then the second and the third row will become identical. So out of the n determinants that arise, n minus 1 of them are 0, only the last one will remain. So what the result is, you keep all the first n minus 1 rows intact and differentiate the last row. That is exactly what you get. This is exactly what you will get. This equation, this determinant. So you get y1, y2, yn, y1 prime, y2 prime, yn prime, etc. N minus first row will also be the same. N minus first row will be yn to the n minus 2 derivatives, etc. The last row, instead of the n minus first derivative, you will get the nth derivative. Now y1, y2, yns are solutions of an ODE, right? So it satisfies the ODE. So the nth derivative will be expressible in terms of the previous derivative. So substitute that into the determinant. Then what do you get? See, then the last row, every term in the last row is a sum of n terms. So once again the determinant will be a sum of n determinants, right? All of them will be 0 except one of them, correct? We can now imagine what is going to happen, right? So are you writing down? So the last, so only one of the determinants will be left over. Right? It will be what? It will be minus an minus 1 w. So integrate that equation. You got an ODE for w, no? You got a first order ODE for w. So what kind of an ODE is it? dw by dx equal to what? Minus an minus 1 x w. It's a linear ODE. See, try to integrate it as a linear ODE. Don't try to divide by w. That's not a advisable thing, because the question arises as to what happens at the places where the w is 0, right? So have you finished writing? So let us move on to the next slide. So I think this, I will stop today with this. So there remains dw by dx equal to the Wronskian again into minus an minus 1, right? So dw by dx is minus an minus 1 w. How? The first line. So your last line, so the last row is what? Your y to the n was there. So you replace it by minus the sum of the other things. So each entry in the last row is a sum of n terms. So determinant will be a sum of n determinants. All of those determinants will be 0 because 2 of the rows will be identical except one of them where the n minus first derivative appears. That is exactly the one that Wronskian. After substituting, what will you get after substituting? right, sigma. Now remove the sigma, get the sigma out, no, because each use the property of the determinant. The last row, every entry in the last row, the sum of n terms. So the determinant is sum of n determinants. So you can remove the sigma outside with the coefficient and it will be 0. Right. So now if you solve, now you must solve this differential equation as a linear first order ODE. Don't divide by W and all. Don't avoid dividing. You see, that's exactly why the whole thing was done. So you divide. We did the linear first order ODE in the morning, and we are using it now. So Wx equal to Wx naught x of minus integral x naught to x a n minus 1 t dt as asserted. So this is a very important formula called the Abel-Liouville formula for finding the Wronskian of n solutions of a because otherwise there will be put an indefinite integral, put a constant of integration, evaluate the constant of integration, and you will get the same thing. Okay. Now why is that this formula has a lot of geometrical content to it? You see, basically what is happening is that if you specify, if you think of the column y1 prime yn to the n minus 1 as a point in Rn, then you see, to specify a solution of a differential equation, what does the energy theorem say? Energy theorem says that moment I give you y and its derivative at a point, the solution is uniquely determined. So instead of giving you the solution, I can simply give you the function and its derivative at a point, right? That is, I specify a point in R2. The same thing happens for nth order differential equation. So if I specify y prime, y double prime, y n minus 1 derivatives at a point, then the solution is uniquely determined. So to specifying a solution of an nth order differential equation is equivalent to specifying a point of Rn. Specifying n solutions now is equivalent to saying that you specify n vectors in Rn, correct? And the Wronskian of these solutions will simply be the volume of this parallelepiped spanned by these n vectors, correct? And what does the Abel-Liouville theorem say? That the volume of this, so think of a solution of a differential equation as a point in Rn, simply because the solution is uniquely given. The solution, I can take the solution, first derivative, second derivative, third derivative, n minus first derivative, and I can write out a point in Rn. Conversely, if you give me this specification at a point, then the solution is uniquely determined. So the solutions are in bijective correspondence with these vectors y of x naught, y prime of x naught, y double prime of x naught, etc., etc., y n minus 1 x naught. So I can think of solution of a nth order ODE as a vector in Rn or as a point in Rn, correct? So you are giving me n solutions, exactly n, and in other words you are giving me n vectors in Rn, and the Wronskian is giving me the volume of the parallelepiped spanned by these n vectors. And the Abel-Liouville formula tells you that as time evolves, what happens to the volume of the parallelepiped? If the volume of the parallelepiped is w of x naught to begin with, later on it is w of x, and w of x is w of x naught times exponential of minus integral a n minus 1. Suppose that a n minus 1 is 0, then the exponential term is then the exponential term disappears, it becomes 1. So you simply get w of x naught equal to w of x. The volume doesn't change. That's exactly what happens to the harmonic oscillator, right? Y double prime plus y equal to 0, there is no y prime term. The y prime term is not there in the differential equation. So that is that is an important example where the volume will remain same. So when an minus 1, when the n minus first derivative term is not present in the differential equation, then the volume will be preserved. This was the original way in which Liouville thought. This is very closely related to the theorem in fluid dynamics. What is Liouville's theorem in fluid dynamics? It says that when the velocity field of the fluid has zero divergence, the flow is volume preserving, and you call such a fluid an incompressible fluid. That theorem follows from this theorem. So it's exceedingly important theorem, and it is directly relevant to engineering. So I'm again pointing out very serious relationships between what we are doing and okay. So we'll continue tomorrow. We'll begin with a quiz.